Yeah, thank you for the introduction, and certainly thank you for inviting me to speak. I'm just so happy to see many old friends here, and also it's my great pleasure and honor to share my research with you. So over the years, as some of you know, like my group has been working on very diverse visualization problem, from visualizing software development process to visualizing the lifespan of supernova. Yeah, but these days, like everybody else, most of my students want to do something with AI machine learning. Yeah, so some of them working on like how to use AI machine learning to assist data visualization and analysis work, and others work on how to make visualization design to help enhance the usability and the performance of AI-based systems. And so today, I mainly want to talk about what my team has been doing with AI machine learning. However, before that, I would like to point out there are visualization works that cannot be replaced by AI machine learning. And that kind of work still require like a long iterative design process. And I will give you two examples to show what I mean. And first example is, in fact, this plankton table, which is an interactive visualization exhibit we created together with the Exploratorium, a science museum in San Francisco. So this exhibit is still on display today, and it has been played by several millions of museum visitors. The design of this exhibit was made with a close collaboration between my group, domain scientists who provide the data, and also artists and exhibit specialists at the Exploratorium. And this whole exhibit, we put in time to design and develop and test, and this long process took more than a year. And we didn't use AI machine learning at all through this process. As some of you might know, making a museum exhibit for the public presents many unique challenges. I mean, first, museums are a free choice environment. The visitors are largely motivated by their personal interests. And so we want to design an exhibit that is visually appearing to the visitor, and then also can quickly engage them, because there are so many competing exhibits at the museums. Take the Exploratorium as an example. They have more than 100 exhibits on a day, right? And then the time each visitor would spend on one exhibit can be on the order of, say, minutes to or a few seconds. So we therefore need to prioritize the data in a way that the user will not only come but also spend enough time to explore, right? To learn what we intended them to learn. The museum visitors include like school kids mostly, and also adults at the various ages, and they have very different background, right? And very level of scientific knowledge and visual literacy. So it's really challenging, like how you design this exhibit, right, such that everybody can actually get something out of it. And so we actually went through multiple design as I show here, right? And over this like more than a year time, and each design we actually did a very serious evaluation using real museum visitors. And finally, we derived this design in which we decide to use a tangible things, which is more like a wood frame, like I show here, and then with a piece of glass acting as a magnifying lens. But it's certainly it's not a real magnifying lens, but then there's a tracking underneath, and then as the user move this around, they can see detail in this particular region. And such tangible device certainly attract kids to play, right? And so it worked really well. And then I have this another example, which has to do with this ongoing project we have on communicating and achieving water equity. So I'm on this project, and then in this project, we want to develop ways to manage water and to balance competing needs. So California has the largest water system in the world to move water to where and when we need it. And like between agricultural, city, and the environment, there really not enough water, right, to meet all the demands. So we want to not only develop way to better manage water, but also we want to communicate with different stakeholders and the general public about, there are actually different scenarios of water allocation and water equity. So the scientists we work with from ecology, they have a way to show some of the information using so-called existence plot, basically showing the probability of meeting, in this case, water demand. Right? So here we see 4 existence plots for 4 different regions in California. However, when we want to communicate with the general public, this probably won't work very well. So my team is responsible for such visual communication task. And so we attempt to create like an interactive app for the general access by the public. And so we want to think of visual metaphor that will work well, like to use as like a glyph in the interactive visualization application. So we started with this water bucket design. And then we later switched to this water droplet design. Basically, we try to show the same information, like how much water, like meeting different demands. But then we finally, end up with this water bottle design. And that's because through this design process, we consult many people, and we found that the regular shape of this water bottle design can serve better, because the irregular shape of the other two could mislead the user, about they're interpreting water level. So for the regular shape, then like say 2 times height we equal to 2 times volume, for example. So so this is like what we did. Also through multiple steps of this design process, in which we didn't really need AI machine learning. So I just wanted to show these 2 examples to everybody, like just to remind ourselves there's still work that we need to do, which you know, we don't really need AI machine learning to do well. Yeah. Okay. So in the rest of the talk, I will give samples of my work. First, on using AI machine learning to support visualization, and then on using visualization to enhance AI machine learning. Yeah. So one kind of data we work a lot is network graph data. Visualizing graph and networks is widely needed in many areas of study, such as social science and biological sciences. To visualize a network, as many of you know, we must first choose a layout method. But then there are many, many different layout methods. Furthermore, computing each layout for a large graph fully could be very, very computationally expensive. And then, you know, to review all this possible layout result is a significant cognitive load for most users. Okay. So here I just show some of the early work we did for network visualization. But what we did is we applied graph neural network to train a generative model for constructing a 2D latent space of layout by learning from a collection of example layout for the given graph. So as you can see, here we have this resulting latent space for this particular graph, and this is actually a continuous space, right? So based on the given example layout, we can have basically all the possible layout, right, between those given layout, and the user can intuitively explore in this space and pick the desired layouts. Okay. And here is another example. This is just a simple, like a mesh network, and it's actually 2D, right? But then it's quite impressive. The machine learning model can learn to lay out, kind of creating this space in a way to build a 3D rotation of this mesh, yeah, which we didn't expect. Okay, so the other kind of data my group has also worked a lot, work on a lot, is volume data. So my group has introduced many ways of visualizing volume data more like efficiently or more expressively. But then, as you know, rendering large volume data at a high quality still computationally expensive. So to enhance the usability of volume visualization further, my group has been investigating like what AI machine learning can offer, right? And for this line of research, my student David Bauer, who actually originally from Vienna, from TU Wien. Yeah, so he has been playing a leading role in this research effort, and he has developed different ways to improve volume rendering quality and the performance using machine learning in, here I want to show in 3 different spaces. So first in the image space, with his approach, he only needs to render a small fraction of the pixels, like 10%. And then which 10% can depend on, for example, eye tracking. Right? And then use machine learning to fill the rest of the image. Right? So he employed a 2-stage convolutional image reconstruction network. And this network can be trained once and then applied to new volume data. And second, in the world space, to achieve global illumination at affordable cost, he replaced tracing secondary rays in path tracing with constant time photon field inferences. And this neural network can be trained like instantly upfront. Okay. And thirdly, in the path space, he used Gaussian splatting, which is a very popular method now, to train the radiance distribution used as a radiance cache. He can then achieve better rendering quality by replacing low contribution rays with the cache radiance value. Okay, as you can see, some of the image looks like the quality is really nice. I think that from my angle, it doesn't look right because the projector, but then hopefully from your angle, it looks better. And I also want to mention the other piece of work, which is also very recent. So making expressive volume visualization can be a very tedious task, which require like very careful materials mapping and illumination setting. So actually inspired by Eddie Grower's work, we recently also work on expressive multi-material rendering using, in this case, stable diffusion model with illumination control network. And we also make it easier to author different material with natural language prompts. So according to users' text prompts, the model generates a grid of materials maps lit from different directions. And from this map, the specified material can then be synthesized to provide coherent, realistic rendering of light interaction with the material surfaces. And we can use the same material maps generated by the diffusion model to extract textual information. Here we see 2 examples. So one is in Ruby, the material is only single material for this Buddha model. And this is a mechanical hand. This one is impressive because we have around 10 different materials. We can easily specify what we want, and we get this like really cool picture. Yeah, I hope you can see the detail. Excuse me. Okay. Next, I'm going to talk about something very different. Now we're talking about how we can help enhance AI machine learning based system. So machine learning model validation is an important task, and conventional evaluation based on models overall performance, like accuracy, can hide some inherent problem. For example, a model, say, with overall accuracy like 98, 99%, may still perform badly on some data subgroup, data subsets. So we developed ways to identify such data subgroup which cause poor model performance. Okay, and then we also provide visual analytics method for the user to determine the root cause of underperformance for model validation and performance improvement. So in machine learning, such data subgroup are called data slices. And the data sample in the same slice usually share some similar properties. So we have made different interface design for such slicing-based model validation task. And you can see here, I just show the interface of these two works. And both also show views or visualization of the identified data slices. So what I'm going to do is just to show a short video so you can see a more complete presentation of the work. It's very short, done by my student.
Machine learning is used more and more in real-life situations. Therefore, it's crucial to thoroughly evaluate these models, making sure they work accurately and efficiently. One method that has shown a lot of promise is data slice finding. It tests the model's performance at specific data subsets, allowing us to understand how the model works under different scenarios. However, data slice finding still faces some challenges. It can be expensive and time-consuming to get the metadata you need to calculate the slices. Furthermore, it takes a lot of time and effort to figure out the root cause for the data slices problems with current methods. These challenges are particularly difficult for vision tasks, where the data is unstructured and don't always contain metadata. We propose Attribution Scanner, a visual analytics solution to validate image classification models. Without relying on metadata, our tool generates interpretable data slices that can be explored in our system, facilitating the discovery of model insights. Our method uses GradCam to create interpretable data slices, which provide insights into the model failure cases. Our framework also summarizes the data slices for easy understanding and allows model iteration, closing the loop in the ML development cycle. Our data slicing approach leverages GradCam to extract a weighted feature vector, which captures the most crucial image features for a model's prediction. Next, we cluster the weighted feature vectors, creating data slices that are easy to understand by data scientists. Exploring data slices one image at a time is very time-consuming. To facilitate this process, we invent the data slice mosaic visualization that captures the main patterns contributing to a model prediction. For each data slice, this approach summarizes the feature attribution within the slice via feature visualization. With our system, the user can easily identify and annotate spurious correlations in the data and annotate them with a few clicks. This annotation is automatically propagated to all slices. For example, consider a hair color classification model. If the most discriminative feature is the mouth, the model is focusing on the wrong portions of the image, creating spurious correlations. The spurious slices can then be mitigated by retraining the neural network using a core risk minimization approach, which adds noise to the spurious features based on the data slices. Our interface consists of three main parts. In the slice table, we allow users to explore and rank the data slices based on slice metrics. The slice mosaic view shows a visual summary of the data slices. Finally, the slice detail view displays the individual images and attributions from the selected data slice. Let's see how our system can be used to understand and mitigate.
Okay, I think you get enough idea. So let me stop here and switch to. Okay, wait. Okay, to the last part actually. For this last part of my talk, I'm going to share with you our recent work on addressing the reliability of AI-based systems, specifically of systems using large language models, okay, LLMs. So LLMs and the prompt engineering have shown their potential in almost every application scenarios. And it has drawn great attention from us, right, visualization and HCI researchers. And for example, there are over 100 publications about LLMs in last year's ACM Chi, as many of you know. And in those papers, LLM are applied to, for example, mental health care, creation of virtual world, or simulating user for app testing, and others. Okay. So while LLM are so promising, their reliability is unclear, as LLM can give us inconsistent result or incorrect, inaccurate result. So therefore, how to enhance the reliability of or the usability the LLM-based AI system is a timely research topic for us, a visualization researcher. And there are many research opportunities for us, in fact, and I'm just going to mention a few here. First, LLM can process and analyze, for example, a large collection of text data much more quickly than human. But we don't want to just blindly accept what the LLM give us, right? So the problem is that it's hard for a human user to evaluate its output, from the output from LLM directly. So we need a way for the user to assess and improve the quality of LLM outputs. And second, LLM users who are domain expert often want to incorporate their expert knowledge when they use the system. And so how do we better support prompt-based interaction of LLM for the user to integrate their expert knowledge in the prompt? And third, the user of LLM-based system may have diverse background, right? Hold a particular value or have some personal prejudice. It would be better if the LLM-based system, for example, in here I mentioned counseling chatbot. So such counseling chatbot does not provide the same response to all users. That is, its response should not be simply based on the training data, right? Ideally, its response should be generated through interaction with the user. Okay. So what would be such an interface be like for the user to better express herself, right? And fourth, the performance or the capability of LLM-based system is often assessed with some benchmarking, right? That's what in computer science we often do. We do benchmarking for this and for that. But in fact, it's better to evaluate the capability of an LLM-based system through a user-directed process on practical usage, in the actual usage. There are definitely other topics that, other problems that we could address. But here I only mention this few. And to address the needs I have just mentioned, the general approach is basically a visualization directed human in the loop process. And based on our experience, it's actually can work very well and becoming very helpful. So my group has worked on some of this design, and we have worked. Basically, we have produced some design for all these four I mentioned here. But today, I only have time for touching maybe the first two. Okay. So the first one, and we're looking at the text summarization. So for text summarization task in various domains, so LLM today can produce output that surpass humans' performance, right? We mentioned that earlier. And then in particular, like, how do we evaluate and, and then possibly, improve the summary at the data set scale? Here, data set scale means we are summarizing a large collection of articles, say news articles, and we want the quality of the summary uniform, right? But then if you manually, right, evaluate the prompt and the resulting summary, it's just simply invisible. Right? So, and previously, NLP researcher, they use some quality matrix, such as the blue and the red here I mentioned, to quantify the quality of the generated summary. But then now, such matrix fail to evaluate or distinguish between state-of-art models such as LLM. That is, as LLM's output exists human-level performance, automatic evaluation based on quality matrix has reached its limits. And so we address this in our recent work, in which we support human-in-the-loop evaluation of the text summarization. And so for this particular text summarization problem, we introduced AWESOME, we call. It's a feature-oriented evaluation workflow that use feature matrix derived from computational linguistics. And this feature could include aspects such as readability or complexity of the summary, and formality and the naturalness, right? So readability has to do with like the length of the summary, and then the length of the sentence and commonality of the words used. And naturalness means like how the text reads like human written. Yeah. And so essentially, Awesomes support user to decompose their summarization goals into a combination of this feature matrix, right? They basically choose a feature configuration. So then the evaluation become more systematic and lead to more actionable insights. Okay. And see, okay, yeah, here. So the Awesome workflow mainly consists of 4 steps. Yeah. At the beginning, by default, the system generates summaries with diverse features. And the user, in step 1, the user select a subset of the feature best characterizing the summarization goal or summarization quality the user like to achieve, right? And then in the second step, the user finds summary example that have the desired feature properties. And then in third step, the user revise the prompt with the goal to make all the summary. Remember, we're talking about summarizing, right, a large number of articles here. And to make all the summary matching the desired feature properties. And in the fourth step, the user inspect the new summary in terms of the feature score and refine the prompt as needed. Okay. And here is the overview of Awesome interface. There are 4 parts corresponding to each of the 4 steps I just described. So the user follow this 4 steps using each component in order. The top part is mainly for feature selection and comparison, while the bottom part is for writing, refining, and evaluating prompt. On the side, we have the document list that show the articles to be summarized, as well as some recommended article according to the user selected feature configuration. Like the system identified some article and summary better match that. And then if user, after user examined it and agree that's really a good representative one, the user will use that as like a ground truth in the following step, yeah, in following process. So again, here, let's look at a short video to get, I think my student can present better than I can, and they give a little bit more information here.
In this video, we introduce a new workflow for prompt evaluation, which we titled Towards Dataset Scale and Feature-Oriented Evaluation of Large Language Model Prompts. Recently, LLM prompts have enabled non-technical people to customize chatbots without coding, democratizing a wide range of automation tasks. However, writing and evaluating prompts is still non-trivial. Previous works have identified 5 challenges in prompt evaluation. Evaluation is opportunistic, manual, multi-criteria, dynamic, and unactionable. These challenges are amplified as the evaluation scales up to dataset scale, where thousands of data points is involved, which are still underexplored. In this work, we report findings from a pilot study on the challenges and design implications in supporting dataset scale prompt evaluation and introduce a feature-oriented workflow to address these challenges. We develop a visual analytics system, Awesome, that supports the workflow for text summarization, combining computational linguistics, cluster analysis, intelligent agents, and interactive visualizations. We present a case study and practitioner review to evaluate our system, report implications for future directions in prompt evaluation and human-agent interaction. Next, let me introduce the feature-oriented workflow. The workflow consists of 4 tasks: feature selection, example sourcing, prompt refinement, and evaluation for refinement. Let's walk through an example in Awesome to see these 4 tasks in action. Our user, Alice, is a middle school teacher who wants to customize a chatbot that can summarize sports-related news articles for teenagers. She types in the feature recommendation panel how to make the summaries appeal to teenagers. The chatbot responds with a set of feature configurations. She checks their definitions and correlations and then adjusts the sentiment to positive. Then, the system recommends a cluster that best fits her goal. She looks at the feature distributions and makes some adjustments, which narrows down the green bubble representing her goal. She inspects the examples in the recommendation view and adds 2 of them as ideal examples. Then she uses the prompt editor view to write a first prompt and then executes it on the validation set. The bubble plot uses bubbles and curves to visualize evaluation results, where the dark gray bubble represents current prompt performance, the light gray bubble represents previous prompt performance, and the green bubble represents the goal. The curves connect individual validation cases from 2 versions of prompt and are colored in yellow if it is moving closer to the goal, or purple if moving further. From the plot, Alice can see that the current prompt is much better than the baseline, but there is still room for improvements, as the dark gray bubble is still not fully overlapping with the green bubble. She inspects the dot plots and finds that formality and sentiment is not being fully satisfied. She gets suggestions from the system on how to improve her prompt, and the new prompt is even better. She uses the test button to execute the prompt on the whole data set, and it indeed has a better performance. This example shows that our system effectively supports prompt refinement and evaluation at dataset scale for text summarization. The system is also evaluated with practitioners from various backgrounds.
Okay, let me stop here. I think you get enough idea with that examples. Hopefully, maybe move on.
In this video.
Yeah, okay. So, with this work, we show the value of human-in-the-loop visualization directed evaluation with, the example and show in the video too. And we also show how feature matrix are used to focus on specific aspect of the summary for more targeted evaluation. So instead of relying on some simple score like pass or fail, our system Awesome provide a detailed characterization of the summary feature like readability. Right? And in addition, by leveraging the same feature matrix, LLM can potentially identify, say, areas of deficiency, right? And ask the user for verification. And this pretty much foster a collaborative mixed initiative interaction. And that also basically suggests like how we might want to design the interface differently. So overall, such feature-oriented evaluation provide a more flexible, interpretable, and collaborative framework for text summarization at dataset scale. And I also want to mention, in often we use rather conventional visualization design. And our future work may include the design of novel visualization for better characterizing some of the feature of interest. Right? So, yeah, okay. So I want to talk about the second work. And so first I want to mention that, so this is an more kind of ongoing effort. My team has been collaborating for like different projects, collaborating with researchers from environmental science and ecology. And this researcher regularly conduct like large-scale interview and surveys of some targeted cohorts. And for example, one group of researchers, they recently interviewed residents in an island called Ruidao, okay? And it's like next to Taiwan. And they, for the study, they want to find out how certain, say, resource allocation and policy changes may impact the residents in the island there. So previously, they will manually review the interview result. And then they will try to identify important factors and the relations between those factors based on a model. In this case, for environmental science, it's called DPSIR. Okay, you can see there's they want to identify driver, pressure, state change, impact, and response. Okay. And certainly also based on their expert knowledge. And like such framework is, as I mentioned, commonly used in environmental science study, right? To assess and manage environmental problems. So LLM is perfect for such text mining task, right? And, or typically we call it a semantic analysis task. So, but then why we use LLM? How can we allow the user to effectively integrate their expert knowledge in this text mining and analysis task? And this is typically like a progressive refinement process, because they kind of explore, right? They can review and explore what they have, and then try to identify certain important factors, and then they come back and forth. They want to, based on that framework, the DPSIR framework, they want to build the DPSIR taxonomy. They want to make it more complete through such a study. Yeah. But then in order to use LLM, there are some challenges to address. First, like, how do we allow the user's prompt incorporating their domain knowledge, right? And then second is by prompting with LLM, right, the expert knowledge can be externalized, but we still need a way to assess whether the LLM correctly understand the expert knowledge and then applied it in, right, the further processing of the text data. And furthermore, expert may express their knowledge in somewhat different way, right? Because we have multiple users, it's not for a single user. And then how they express their knowledge may change. through the process, right, as they gain more new insights. So we need to take all this into account for our design. So to address these challenges, we have developed GreenMine. It's like a interactive text mining pipeline. And so GreenMine segment corpus into snippets first. And the snippet goes through and this interactive prompting pipeline consistent of 3 steps. And so the indicator, variable, and link, which is relation, okay, identification. So with GreenMine, the environmental expert, the scientist, can use the visualization provided to explore the corpus, evaluate the prompt performance, and refine the to improve their DPSIR taxonomy. So this is the interface of GreenMine, which consists of 4 parts. Similar to the previous design, you can see you have place for the user to enter prompt and then examine some results visually. And so in the entry panel, the user can express their knowledge in natural language and refine the prompts. And then the result prompts show the mining results either in a simple list or in the in this uncertainty visualization we designed. And then the comparison panel is basically the same as the result panel, so user can compare the results, some results side by side. And from the result panel, user can quickly navigate the corresponding document in the document panel to validate the mining result. That is, the user can always go back to the original document if they wish. And in the uncertainty visualization here, you will also see in the video, each dot is a snippet, and the dots are organized by topic. The visualization show what the interviewee talk about, in this case, about driver, and the user can modify the definition of driver here and in prompt, right, in order to reduce, their goal is to reduce uncertainty. And the uncertainty is based on a consistency measure. So toward the middle, this is like a radial layout. Toward the middle, it's more certain, right? Away from the middle is more uncertain. Okay. So again, we have this video. A short video you can watch.
In this work, we introduce a system that supports visual text mining with progressive taxonomy construction for environmental studies. In environmental science, the DPSIR framework is proposed to study and communicate the complex relationships between societal and environmental factors. In practice, scientists will collect, organize, and analyze sources of documents to contextualize the DPSIR framework, which is laborious and inefficient. Moreover, there are some unique challenges in automation support. First, the DPSIR taxonomy is dependent on the research questions and studied region, which makes it hard to design a universal taxonomy. Second, scientists usually progressively update the variables as they gain deeper understanding about the ecosystem, which makes evaluation challenging. To address these challenges, we work with environmental experts and design a system that supports interactive text mining based on prompt engineering. For the first challenge, we design a 3-step prompting pipeline that allows the experts to adjust the taxonomy to fit the context. For the second challenge, our system supports evaluation and exploration with an uncertainty chart, which plots uncertainty and the semantic similarity on the same plot. Users can use this chart for evaluation and get actionable insights on how to refine the taxonomy definitions. Next, let's see how the system works with a case study. Our collaborating expert, Jason, is studying public opinion on the environmental policies for Liudao in Taiwan. He has collected a corpus of interview transcripts and wishes to refine an existing DPSIR taxonomy derived from the literature. He imports the corpus and the initial taxonomy into the system. He can execute each of the steps using the initial taxonomy and refine the taxonomy definitions. In addition to a simple list view, he can use the uncertainty chart to inspect the uncertainties and topics at a glance. He can also use the side panel to compare the results side by side. For example, during indicator identification, he finds an outlier snippet in the drivers that has high uncertainty. He inspects the snippet and finds that the interviewee is talking about a historical event that causes the residents to value culture security. He believes that this is something that is often overlooked in the literature and adds cultural security to the driver taxonomy. The system also provides several auxiliary visualizations. For example, he can use the keyword cloud to inspect miscellaneous keywords, or use the link graph to inspect complex variable relationships in a snippet. He can also quickly navigate to relevant conversations in the document panel. After several iterations, Jason is satisfied with the taxonomy and the insights he gained from the system. To provide an overview of the mining results, the DPSR graph aggregates all the variables and links into a graph and supports progressive disclosure. Jason can use it to communicate the insights he gained, such as the most significant variables or some unexpected relationships. The design follows existing diagrams in environmental studies, which is ideal for collaborative discussions among environmental experts. We evaluate the system with an expert review and find several promising potentials of the system. Moreover, the technical challenges and solutions in developing the system has broader implications for other interactive text mining systems. We discuss these lessons learned and future opportunities in the paper.
Okay.
In this work,
So I guess it actually summarized very well for us. So basically, this work effectively addressed the limitation of LLM on knowledge-intensive task. Okay, because an LLM-based system either must be trained with sufficient data, right, good data, or the user, us, right, must be provided a way to incorporate our expert knowledge, right, our intent and our knowledge when using the system. So again, human in the loop evaluation, visualization, feedback to guide the prompt refinement is critical part of this system, GreenMind. But to use GreenMind, we had to, and with our current design, okay, we had to give the user, the scientist, extensive tutorial. We have to teach them how to use it. And so for like new user, right, if they didn't take the tutorial, they might have a hard time to use the system. And there's something that we need to think more about, how to come up with better design. And yeah, so yeah, basically this we hope like by accumulating all this experience working with user of AI-based system, like what I have shown, that we can learn better, like through all this evaluation and the finding we have, the insight we gain, we will be able to design better system, more generally applicable, right, to other application scenarios. Okay, so I have given many different examples, I'm a bit ambitious. Hopefully it's okay. So let me conclude. Basically, human AI collaboration is the train, right? And hopefully I convince you visualization is the best interface for human AI teaming. And so while the AI and machine learning, right, becomes so pervasive, right? And so pretty much everybody's working on something to do with AI machine learning. And for us, right, visualization, HCI researcher, there at the same time, right, there are tremendous research opportunities for visualization and interface design, and which can better help enhance the usability of AI based system. But also, yeah, it's not only the better interface and visualization design can help improve the performance of the system, but also help enhance the performance of human user, right? Yeah. So, and then again, I also want to take this opportunity to point out again, while AI can assist with many tasks, research tasks like visualization design still cannot be completely done by AI machine learning. Okay, so thank you for your attention. This is my conclusion of my talk. And I want to mention these are the students who did all the work. And what I presented today, either we already published or to appear in some journal conference, or we're going to submit. So I'm happy to share with you. If you're interested in particular work, I can send you either the paper and or the video we have. Yeah, thank you.
Yeah, thank you very much for this really cool insight into your work. I think you mentioned many, many very important things. Yeah, we have time for questions. So are there questions, I guess? Yeah, please.
Yeah, I have a question, a real-life situation. Being in California, in the drought situation, was your instinct with the water project that you had, were you called upon now after this horrific disaster to, like Lidau, to have interviews with the affected people and then use that data and to find policy-making solutions? Has your institute been asked to be involved in that?
That's what we have been doing, what we're supposed to do. But then it's, as you know, it's a very complex problem. It's not just human factor, but also the nature that we cannot control. Like this recent incidents, right? It's partly due to the weather pattern, right? Like very wet season followed by very dry season, but then definitely we should do more, right? And then possibly with AI machine learning, right? And we can do better prediction and then to do better prevention. Yeah, but we've been working on that. Yeah, for sure. Yeah. But then I'd like to add that, sorry, so my team has the opportunity to work on this communication job, right? Try to communicate with different stakeholders. So from like scientists to general public. And that's really interesting, but also very challenging task. Something we're still learning how to do well. Yeah.
Fighting misinformation.
Yeah, exactly.
Other questions? There must be more. Yeah, please.
So in the end, you said something what I found quite nice is that to interact with LLMs, we have to turn to visualization, which I fully agree. And do you have any other works or ideas currently to improve this? Because LLMs are notoriously text-based, so we have to find ways to visualize them. Do you have any approaches currently in the works other than those great ones you've shown?
You mean, do I have other projects on this similar topic which we design better visualization interface for people to use LLM-based system?
Yeah, in general, just approaches to, for example, because we have text output and we usually do maybe embeddings, as you've shown, or score the text output, which you have also shown, but do you have any other approaches or ideas to work with the text output, in a sense?
Yeah, it's there are two directions, right? One is more kind of generally applicable system, which is even more difficult to work on. But then there's also more kind of domain-specific, task-dependent, right, design that we can do maybe better. So we work on both, as I show here. But then, right now, I cannot think of another example that I can verbally describe well, like what we actually did to make it better. In fact, the two LLM-based system we work on. Oh, okay. Now I'm thinking. I'm trying to think because it's just like there's all these different projects. So we also work on, yeah, it's really not easy. That we work on the, as I mentioned in some of these other challenges I identify. We try to address this one problem, like the user, they have different value system, right? They can be very subjective. So we try to address that somewhat. We basically design this system, allow people to kind of review some news article, and then to determine whether their belief, right, their understanding, match what the media, right, give them. And then basically try to identify if there's any bias. So we come up with some way to address that, and I mean visualizing design. But the reviewer didn't like it, so I think we still try to publish that work. But I'm happy to share that paper with you if you like. I think it's in archive, and that's actually I like that work. But then I guess the visualization was not novel enough. Typical. but it's important, right? As many of you know, you want to keep everything simple, right? Simplicity is the key to make the interface effective.
Thank you.
Yeah, Silvia.
Hi, thank you for this inspiring talk. And I mean, your topic was called AI assistance and mixed initiative and human in the loop. Huh? You mainly, I mean, this was your topic, AI assistant.
Yeah, I changed
no, my question, wait. My question is, you mainly focused on large language models, but AI is a little bit broader than large language models. Yes. Can you tell me some vision with other AI methods or machine learning methods the visual community, the visualization community can benefit of? Just a visionary, yeah? I mean, LLMs, yeah, but there's more.
Yeah, true. I have to think. So, yeah, I already, actually I had a great concern, like I tried to show too many different pieces. And But yeah, at the end, I choose to focus on LLM-based system. Otherwise, it's almost impossible to give the presentation. But then, yeah, we work on other problems using other AI machine learning models. And like one problem we work on, actually we work in the healthcare and medicine domain also. Actually, that's a significant part of my current efforts. And I also kind of surprised myself, like I didn't mention any of that. And so it's good you asked this question, I can mention it a little bit. So in those projects, like one project, we try to, we're part of this large team with those medical doctor, right? It's including surgeon. So we try to utilize AI machine learning method to support surgery, real-time surgery. And so we need to basically reconstruct 3D visualization from different modality, image modality data. And we need to make sure it's accurate enough. So far, they are not good enough. Okay? Because it's, first we want to, we have data from like this stereo imaging, and then so we have a pair of image, but still not good enough to give us like the very accurate reconstruction. Especially we're talking about real-time visualization during the surgery. So we can probably come up with more accurate result, but it's just gonna take too long. We need to constantly retrain the model. That's still not feasible now. And then we also need to project different, because they try to use multiple modality data to assist the surgery. So we essentially gonna create this 3D reconstruction and then project other modality data onto that 3D surface so they can see better. Basically, they can only see, right, like what the camera allow them to see, but then we want them to see what underneath, like remaining cancer that they need to remove, for example. But we try this we work on this for like over a year. It's still not enough. Like it's not fast enough. It's not accurate enough. So yeah, there's still a lot we need to work on. Yeah, this is just one example. I could give it another one over coffee break, I guess.
Thank you. Thank you very much.
Are there more questions? Don't be shy. This format here is also like, we would like to encourage you to ask questions. Also the students in the room, yeah, please, don't be shy.
Or everybody want coffee?
Thank you for your presentation. My question is, like, you talk a lot about AI reliability, and I think it's very important. But what do you think, is this like AI reliability, is it like a common trend in research or in general in AI? And what do you expect in that domain to happen? Like, will AI get more reliable in the future, or will it be less reliable?
Yeah, that's not just our goal. I mean, we just see that's a problem that somebody need to address, but we're not the only one, right? Because not just visualization work can maybe help in some way. Like people in machine learning, AI, they work very actively on this problem. And as we say that the performance of AI system largely depends on what the training data they have, right? They use. So, but then also people try to make the machine learning model more transparent and more explainable, and that also give us, right, the opportunity to do something. And so it's I mean, for casual tasks, right, it's not big deal. Like almost, I think everybody in this room use ChatGPT or something equivalent, right? And it's generally helpful. But then for some really critical task, like or knowledge-intensive task, right? Like the real-time surgery support I mentioned, right? So you cannot tolerate any inaccuracy or unreliability. So I think the problem is always there, that we just like for some application scenario, you can accept, say, 90%, right, accuracy, but then others need to be almost like perfect, right, 100%. And then there's also, if you notice, so we definitely will rely on AI and machine learning more and more. And then there's a trend to use, basically we use, like daily use machine learning AI system as like an agent, right? And then there's this attempt to utilize multiple agents, right? Each agent, they are good at something particularly well, right? And so then you use multiple agents together to perform some sophisticated task. And then you think about if you're going to design a visualization interface for such setting, right? What would you do, right? Like, what would be the appropriate design? So that's another interesting direction that I just remember to mention. But yeah, to answer your question, the problem is always there. And there are other problems of AI-based system, but then they all pretty much related, right? It all has to do with the performance, right? Trustworthiness, right? Yeah.
You mentioned healthcare.
Yes.
And the example you gave was in the operations.
Yeah.
Are there, and I've heard of research on AI being used to diagnose early onset breast cancer.
Mm.
But do you have any ideas or can you think of any projects that are being used now for healthcare in the sense of healthy aging?
Yeah.
That would be really important.
Yeah. Not particularly about agent, but then we do have another project. It's an active project. So again, I work with a colleague at our medical school. And what we did, it's very interesting. So we have this EHR system, right? The electronic health record system that medical professional rely on, right? Basically, all the information about patient, what the patient receive, and then the condition of patient and doctor opinion, everything is in that system. So it's been long, people try to make use of the information, but then previously, due to privacy, a lot of concern, right? It was hard, but now it's more open, so we get a chance to look into like how we can use the EHR data for individual patients or for like large cohort for a study of particular disease, right? Like cancer or others. And so a lot of people work on that. Actually, they just use AI machine learning to basically, they feed the patient record, right? Like over a long period of time, a large cohort patient, and they learn something from it and use it for prediction. I think somebody here must be doing that. Okay, I'm pretty sure. But we work on something different. We still use EHR data, but then we did something very, very different. What we try to do is to look at EHR data for a large group of patients, but then what we look at is through the EHR system, because the EHR system log pretty much everything. Oh, okay, yeah. So log everything about what the doctor and nurses, other medical professionals did, right? Over this long period of time of treatment of particular patient, each patient. And so we look at the log, And we, based on the log, we build a communication network. Basically, we try to understand through the log, try to understand how medical professionals work together through the EHR system. And then we compare patients who survive and patients who did not. And then we see if the communication pattern different. And we maybe can provide advice to those medical professionals, like how they should work together, or, yeah, so let's give an example.